we have started to learn about the artificial satellite in previous lecture. Now today, in this lecture, you will see a very important example of artificial satellite, and this is called actually geostationary satellite. So geostationary satellite is just an artificial satellite, and it is of great practical importance. In fact, a geostationary satellite is used for distant transmission of radio and TV signals. It is also used to study the upper regions of the atmosphere, weather forecasting, and different earth measurements like gravitational measurement, magnetic field measurement. So these are the important applications of this geostationary satellite. In this lecture, you will learn about what is this geostationary satellite, where it should be, it should be rotating about the earth, and what should be its height from the surface of the earth, or in other words you can say what should be its radius of the orbit. Actually, this geostationary satellite must revolve in a circular orbit, so here we define the radius of the orbit, not particularly the major axis or minor axis as in case of elliptical orbit, because the orbit of the geostationary satellite is definitely circular. Okay. So let us see what is this geostationary satellite. As the word says, geo means earth and stationary means at rest. So if a satellite, when observed from the surface of the earth, and it appears to the observer always stationary, then it is called geostationary satellite. So whenever an observer standing on the surface of the earth observes this satellite, it appears always at rest. And you know about relative motion, how it is possible that anybody always appears the observer to be at rest. This will be only possible when the velocity of the body and the observer are same both in magnitude and direction. Only then relative velocity between the object and the observer will be zero, and that object will always appear at rest to the observer. So definitely this geostationary satellite will have the same angular velocity as that of the angular velocity of the earth rotation. Or in other words, you can say that the time period of revolution of this geostationary satellite must be equal to the period of Earth's diurnal rotation, which is actually 24 hours. So if the time period of revolution of this satellite will be equal to 24 hours, then its angular speed will be same as that of the earth, and this satellite will always appear stationary with respect to an observer standing on the surface of the earth. Actually, this depends on the height of the satellite, so that this condition will hold. So if the height of an artificial satellite at the equator above the earth's surface is such that its period of revolution is exactly equal to the period of rotation of the earth, then the satellite would appear stationary over a point on Earth's equator. This is a very remarkable fact. This satellite must be above the geographical equator of the Earth. You will learn after this, at the end of this lecture, that if the satellite will be in an orbit which is not just above the equator, then it is not possible that the satellite will always appear stationary with respect to the earth. So the orbit of the satellite must be in equatorial plane. Okay, And I have shown this fact in this figure. You can see this sphere which you see in this figure represents the earth, and this omega e, this is actually the angular velocity of the earth. Okay, angular velocity means velocity of rotation of the earth, whose time period is 24 hours. And we consider that in equatorial plane a satellite is revolving around the earth. This small sphere which I have marked here, this represents the satellite, and this its orbit is circular, and it is in the equatorial plane of the earth, and its angular velocity is omega s. Now if this omega e and omega s both will be equal in magnitude and direction, then you will see that the satellite will appear always stationary to an observer standing on the surface of the earth. You can easily see. I have shown here that the angular velocity of the satellite with respect to the earth, WSE, represents angular velocity of the satellite with respect to the earth. And you know this WSE, which is relative velocity of the satellite with respect to the earth, this will be equal to omega s minus omega e. Okay. Now the time interval between its two successive appearance overhead will be what? This t will be equal to, you know, t will be equal to 2 pi divided by omega se, but omega se is equal to omega s minus omega e. Okay, and this will be equal to 2 pi over, now omega s, which is angular velocity of the satellite, this will be 2 pi over ts, where ts is the time period of the revolution of the satellite. Okay, and omega e, this is angular velocity of earth rotation, and this will be 2 pi over te, where te is the period of rotation of the earth about its polar axis. Okay, now you can see this 2 pi will cancel out, and your result will be 1 over 1 by ts minus 1 by t, and after taking LCM you can see this result will be ts times te over te minus ts. Okay, now if you consider that this omega s, that is angular velocity of the satellite, is equal to the angular velocity of the earth rotation, that is omega s is equal to omega e, then it is obvious that this period of revolution ts will be equal to te. And so you can see from this relation that if omega s is equal to omega e or ts is equal to te, you can see this time period t will be equal to infinity. And if time period t is infinity, what does it mean? It means the observer will see that the satellite is stationary at its point, because it will never complete a rotation or revolution. Okay, and that's why we say that such a satellite whose angular velocity will be equal to the angular velocity of earth rotation, or whose period of revolution period of revolution ts is equal to the time period of the earth's rotation, then such a satellite will appear always at rest to an observer standing on the surface of the earth in equatorial plane, and such a satellite is called a geostationary satellite. Okay, so I have mentioned it here. You can see it means the satellite will appear stationary relative to the earth, and such a satellite is called geostationary satellite. Okay, actually the orbit in which this geostationary satellite revolves, that is called geostationary orbit, or it is also commonly called parking orbit. Okay, this is a very remarkable fact, and it is important for objective type of question, that you will be asked that the orbit in which a geostationary satellite revolves is called what? the orbit is commonly called, popularly it is known as parking orbit. Okay. So as I have told you that an artificial satellite which will just appear stationary to an observer standing on the surface of the earth, which is called geostationary satellite. Can this satellite be observed from any place, or can it be lying above any place on the surface of the earth? Answer is no. There are actually three important conditions for a artificial satellite to be called a geostationary satellite, or or you can say an artificial satellite will be a geostationary satellite when these three conditions will get satisfied. And what are these conditions? The first one is that to be geosynchronous. It means what? It means the orbit of the satellite must be geosynchronous orbit, which means for such a satellite moving around the earth, the period of revolution of the satellite must be equal to period of earth's uh, earth's rotations period, which is almost equal to 24 hours. Okay. The second condition is its orbit must be circular. Okay. And the third most important condition is this satellite must stay over the geographical equator of the earth. It must stay over the geographical equator. If this satellite is not over the geographical equator, then it cannot be a geostationary satellite. Okay. Now we will see a very important calculation, and this is regarding the calculation of height of the geostationary satellite from the Earth's surface. Okay, or in this calculation you will also see what should be the orbit of the circular, what should be the radius of the circular orbit of this geostationary satellite. This is a very simple calculation and you can easily calculate it. So let us now consider, this is your earth. This small sphere shown in this figure represents the earth. Okay. And this capital R represents the radius of the earth. O is the center of the earth. Okay. And this bigger circle, this is actually the orbit of your geostationary satellite. And the radius of this circular orbit of the geostationary satellite is a small r. And I have assumed that from the surface of the, this point A is at the surface of the earth on the equator, in the equatorial plane, and from A the height of this satellite, which is at point P, is equal to h. Okay. So in this condition you can say that the orbit that the radius of the orbit, that is a small r, is equal to capital R plus h. You can see the figure. Okay, where you know r is the radius of the earth and h is height of the satellite from the surface of the earth. Okay. Now you know, since the satellite is revolving in this circular orbit, and you know for circular motion a centripetal force is required, because centripetal force acting on the body provides its circular motion. So here actually our satellite, which we consider is of mass small m, that is attracted gravitationally by the earth. If you consider that this capital M is the mass of the earth, then the gravitational force acting on this satellite due to the earth will be what? From Newton's law of gravitation, this will be simply gmm over r square, where this small r is r plus capital R plus h. And this gravitational force exerted by the earth on the satellite provides its necessary centripetal force for its circular motion. So you can easily write the equation of motion of the satellite. You know, for circular motion, the centripetal force F must be equal to ma, and a, which is called centripetal acceleration, that is v square by r. So equation of motion will be F equal to mv square by r. Okay, but F, you have seen, this is gmm by r square, and v I have assumed here vi. This is called velocity of insertion, as you have learnt in the previous lecture. So vi is the velocity of insertion with which this satellite has been projected in its orbit. Okay, now you can see this small m, which is mass of the satellite, will cancel out. This r will also cancel out. Okay, so finally you get vi equal to root over gm divided by r. Okay, and you can also write this as you know, this gm is equal to gr square. Okay, and divided by this small r. Okay, so this is r times root over g by small r. Okay, this is the velocity of the geostationary satellite in its circular orbit, whose radius is r. Okay, now as you have seen that the period of revolution of this satellite, which I have denoted by ts, that is simply equal to te, and the value of t you know is almost 24 hours, although exact value is 23 hours 56 minutes and 4 seconds. But in general calculation we simply take this time period equal to 24 hours. This is actually the period of rotation of the earth. Okay, now as in one rotation in this circular orbit, the distance covered by the satellite will be 2 pi r. Okay, and this distance our satellite covers with a constant speed vi. So when you will divide this distance 2 pi r by vi, you will get its time period. So ts is equal to 2 pi r over vi. Okay, but vi you have calculated here, you can see this will be 2 pi r root over r by gm. Okay, and I have substituted this gr square here at the place of this gm, you can see. So ts is equal to 2 pi r times a square root of a small r divided by g capital R square. Okay, now if you will square this expression both sides, what will be your result? This will be ts square equal to 4 pi square r cube divided by gr square. Okay, and from here you can see easily that this small r, which is radius of the orbit of this satellite, that will be equal to cube root of gr square times ts square over 4 pi square. Okay, now you can see in the all the quantities in RHS have a standard values, all are known. So when you will substitute the values of all quantities in RHS of this expression, you can easily find the value of the radius small r of this of the orbit of this satellite. So this r is equal to what? G, you know, this is 9.8, and radius of the earth, capital R, this is 6.4 times 10 to the power 6 meter. Okay, and 24 hours, t is 24 hours, and you know 24 hour will be equal to 24 into 60 minute, and this will be in, when you will multiply it by again 60, then this will be in second. And after multiplying these three numbers, you will get 86,400. Okay, so I have substituted the standard value of all the quantities in RHS of that expression, and on simplification you will get that this small r is equal to 4.2 into 10 to the power 7 meter. Okay, and so this is actually this much kilometer, this much kilometer. it is almost equal to 42,300 kilometer. So you must remember it. Roughly, we also say that the radius of the orbit of a geostationary satellite is 4200 kilometer, but its exact value is 42,300 kilometer. But roughly, you can remember that the radius of a geostationary satellite, the radius of the orbit of a geostationary satellite is almost 42,000 kilometer. Okay, 42,000 kilometer. Now, once we have calculated the radius of the orbit, now we can easily find what will be the height of this satellite above the Earth's surface. As we have seen that the radius of the orbit of geostationary satellite small r is equal to capital R plus h. So its height above the surface of the earth, that is h, this will be equal to r minus r. Okay, so I have written here, you can see h is equal to r minus r, but a small r, which is radius of the orbit of geostationary satellite, this is 42,300 kilometer minus capital R, and you know the radius of the earth is 6400 kilometer. So after subtraction you will get that the height of this geostationary satellite above the earth's surface is almost 36,000 kilometer. Both of these data you must remember. Height of the geostationary satellite from the earth's surface is 36,000 kilometer, and the radius of its orbit is 42,000 kilometer. Okay. Now you can also see when you will put the value of this r and this r in this result, we can easily find what will be the speed of this geostationary satellite in its orbit. So after substituting all those values, it is found that the speed of geostationary satellite VI is almost equal to 3.1 kilometer per second. And this data is also important and must you have to remember for your objective question. So the three data you must remember. Radius of the orbit of geostationary satellite, which is 42,000 kilometer. Height of the orbit of the geostationary satellite from the surface of the earth, this is 36,000 kilometer, and a speed of geostationary satellite is 3.1 kilometer per second. These are three important data. Okay. Now here I have mentioned a important question. What we have learnt earlier, that will be clarified by this example. The question says, is it possible to put an artificial satellite into orbit in such a way that it will always remain directly over New Delhi? New Delhi, you know, this is capital town of India. So if a satellite will be placed in an orbit such that it will always remain directly over New Delhi, is it possible? And it is also given that Delhi is a place which is not in the equatorial plane. Delhi is not in the equatorial plane. As you can see that the satellite has been placed in such a orbit which is just which appears above this New Delhi, and this place is not in equatorial plane. So in this figure you can see I have shown that the angular velocity of the satellite omega s and the angular velocity of Earth rotation omega e are not in same direction. It means you can see in this figure even if the magnitude of w omega s and omega e will be equal, even after that omega e will be not equal to omega s because their directions are different. So in this condition, the angular velocity of earth rotation and the angular velocity of the satellite are not equal. So the time period Te will be not equal to Ts, and so that the satellite will not appear always above Delhi. So the reason is obvious, since the satellite has been not placed in an orbit which is in the equatorial plane, so that this cannot be a geostationary satellite. So answer is no. Answer is no. A satellite will appear stationary only when the direction of motion and magnitude of angular velocity of the satellite is equal to that of the earth. That is, the plane of the orbit is equatorial with time period 24 hours from west to east. Only then it will appear stationary above a surface on the earth. As New Delhi is not in the equatorial plane, mark it. So it will not be possible to put a geostationary satellite over New Delhi. So any place which is in equatorial plane, above that place this geostationary satellite can be placed. Okay. So I hope you have clearly understand the concept of geostationary satellite, and as I have told you that this satellite is of practical importance, and I have mentioned its practical applications in the beginning of my lecture. I am just repeating that this satellite is used for distant transmission of radio and TV signal. It is also used for the study of upper region of atmosphere. High altitude satellites are used for astronomical observations, or you can say the effects of atmosphere are not present here. Then we can use it for high altitude satellite for astronomical observations. This satellite is also used for weather forecasting and earth measurements. Okay, so after this lecture, the concept of central force in accordance with your syllabus is now completed. Okay, and in the forthcoming lecture we will see something regarding the small oscillations in classical mechanics which has been left. I have provided some videos, but some concepts were not dealt, so I will try to complete the complete syllabus of the small oscillation in forthcoming lectures. Thank you very much.